record it today. Okay. So, why is my mouse messed up? Oh, geez. Okay, there we go. Okay, so welcome to 19th meeting. Today we have black holes. So first, last week, what we had was we talked about the 5 ages of, am I even screen sharing? Okay, yes, I am. We talked about the 5 ages of the universe, which describe the universe from beginning to end. And we use this time scale called cosmological decades, which is a logarithmic scale, meaning that each cosmological decade is 10 times longer than the last. So like in the first era, the primordial era, it goes from the -50th to the 5th cosmological decade. So that's 10 to the -50 years after the Big Bang to 10 to the 5 years after the Big Bang. And so during that era, we have just the very early universe with the singularity, inflation, and cooling. And then the next era, in the Siluriferous era, where stars dominate the universe, and this is the era that we are currently living in. And then we have the degenerate era, where after all of the stars die, all that's left over are brown dwarfs, white dwarfs, neutron stars, and black holes. And then soon enough after that, all of these guys die and all that's left are black holes. And that leads us into the black hole era, where only black holes exist and they are very slowly evaporating in a process called Hawking radiation, which we'll talk about today. And then after all the black holes evaporate, we just have the dark era, which is just like this till the end of time, basically just a bunch of particles floating around. So that is what we did last week. And then today we have black holes. Kind of a lot of subtopics, but I'm not even sure if we'll get through them all, but that's okay. Yeah. So we have like what black holes are, we have the history of black holes, and then we just have these 4 subsections are just kind of like different mathematical descriptions of black holes. And then we have the different masses that black holes can have and like the different types. And then what happens when you go inside a black hole, and finally Hawking radiation, which is how black holes die. And so first, what are black holes? So a black hole is a region of space-time that has such a strong gravitational pull such that nothing can escape from it. They have this singularity, which is a point that we cannot physically describe. That is the definition of a singularity. It is infinitely compact and has infinite curvature. You can kind of see in this graph, the slope of the curvature just becomes undefined as you approach the singularity. So it is infinite curvature. And then black holes also have this point of no return called the event horizon. And if you pass it, you are not coming out. And then finally, the existence of black holes is predicted by Einstein's theory of general relativity. And from that, since we talked about general relativity a few weeks ago, you could kind of get the sense that we'll be talking about like curvature and space-time and metrics and stuff. And we will be, so yeah. So something that is funky about this black hole jargon is that we say that they are no hair. And what we mean by that is that black holes are in a way very simple objects. They can be completely described by 3 things: their mass, electric charge, and spin angular momentum. And we refer to this fact by saying that black holes are no hair, because like a way that you can describe people is by their hair. Like, is it curly? Is it straight? Is it brunette? You know? So since black holes only have 3 parameters by which you can describe them, they only have 3 hairs, and that's virtually no hair. So we say that black holes are no hair. It's very weird, but whatever. Yeah. And then another thing is that you might be wondering is, how do we even observe black holes? Because they don't emit light, how do we see them? So since black holes do not emit radiation, we cannot observe them like we would any other object. But what we can observe are the effects that black holes have on nearby objects. And this is how the famous image of a black hole was taken, by looking at the gravitational effects that the black hole had on the surrounding gas. It was just kind of like this ring of gas, and the black hole was just like this gaping shadow in the center. And so we can observe black holes in the centers of galaxies by seeing their effects on nearby stars. And another way that black holes can be detected is by detecting gravitational waves, if those waves are generated by two merging black holes, because there are a lot of ways that gravitational waves can be created, like merging neutron stars and stuff, and one of them is merging black holes. So that is one way to tell that we know that black holes exist. So a quick section on the history of black holes. So the idea of black holes first started in like the late 1700s, when these guys, John Michel and the famous mathematician Laplace, were discussing the existence of highly compact objects, which they dubbed dark stars, such that their escape velocity was greater than the speed of light. And this is a black hole. And so their discussion of this was largely theoretical, like they didn't have any mathematical descriptions or observations to back their thoughts up, but they came up with the idea. Yeah. And then in 1915, we have Einstein's theory of general relativity, which is the mathematical model that says that black holes are possible. And then after this, throughout the next 50 years, we just have a bunch of people trying to find solutions to the Einstein equation, which is an equation from general relativity. And these, oh, my screen sharing is paused for some reason. I do not know what happened. Uh-oh. Okay. What was I saying? Oh yeah, so we have these different solutions that basically describe black holes in different ways. So in 1916, we have the Schwarzschild solution, which describes a non-rotating electrically uncharged black hole. And then in the next couple of years, we have the Reiner Nordstrom solution, which is another non-rotating black hole, but this one is electrically charged. And then in 1963, we have the Kerr solution, which describes a rotating electrically uncharged black hole. And then finally, in 1965, we get the whole package with the Kerr-Newman solution, which is rotating and electrically charged. Oh, geez, my computer is dying. My mouse is broke, y'all. Oh, geez. Okay. Okay, so now in 1964, we have the first black hole, Cygnus X1, was observed. Hi, James. And so, like we said earlier, this was observed by looking at the nearby effects that the black hole had on the nearby objects. And then in 2016, we have LIGO, which is the gravitational wave detector, first detected gravitational waves, and these specific gravitational waves were generated by two colliding black holes. And then, of course, in 2019, we have the famous image of the black hole. And what I also should have included here is the 2021 image of the black hole with the overlaid polarizations, which we talked about a few weeks ago. Remember, like the video with the British lady? She was explaining like the polarizations and stuff. So yeah, but anyways, so that is just a quick history of black holes. And now we get to move on to the mathematical descriptions, all of the general relativity stuff. This might be a little bit not fun to look at, but it's okay. You don't have to just listen to the conceptual basis of it. It's okay. So recall from the Einstein equation, which relates curvature to matter and energy. And if you solve the Einstein equation, then that tells you basically everything that you need to know about your model. So how do we solve it? So on the left side here, we have R mu nu and R. These values describe the curvature of the space-time. And these values can be calculated if you know the metric G mu nu. So once you have those calculated, you have your left side of the equation. And then on the right side is just kappa T mu nu. Kappa is a constant, so you can easily solve for T mu nu. And that is it. You have solved the equation. Therefore, thanks to this equation, all you need is G mu nu in order to get a complete description of your space-time. And so when we look at the different solutions to the Einstein equation, we're basically just going to be looking at these values of G mu nu. And real quick, do you guys remember like what the metric is? I guess just in case, it's basically like the metric is going to tell you how to measure distances in your space-time. So like, for example, if we have, oh geez, this is going to be terrible. If we have the metric for just like regular Euclidean space, we're going to have -1, 1, 1, 1, and like everything else is just going to be zeros. And so here this is the t components, the time components, the x components, the y components, and the z components. And then again, t, x, y, z. So the metric is just a matrix that describes, it's kind of like your ruler for space-time. So like x is just one unit of distance, y is one unit of distance, et cetera, et cetera. So that is what your metric G mu nu is going to tell you. But in the metrics that we're going to be looking at today, it's not going to be x, y, z. It's going to be spherical coordinates. So like r, theta, and phi. So yeah. Okay. So now we're going to be looking at 4 different solutions to the Einstein equation, basically just their metrics. And each of them are going to be describing like the different types of black holes, which we said earlier, the Schwarzschild metric, the Reiner-Nordstrom metric, the Kerr metric, and the Kerr-Newman metric. Okay, so first up is the Schwarzschild solution. So the Schwarzschild solution just generally is a spherically symmetric vacuum solution to the Einstein equation. So basically, it's just going to be describing the space-time around a spherical object inside a vacuum. So remember how the metric works? We just said this, G mu nu, G00 is the time component, G11 is the R component, G22 is the theta component, and G33 is the phi component. So yes, and here's the little diagram for spherical coordinates again, if you're confused. So we will look at this in depth in just a second, but first of all, Schwarzschild was a beast, okay? So let's just look at this. So in 1915, Einstein published his theory of general relativity. And at that same time, Karl Schwarzschild is serving in the German army during World War II. And as he is fighting in World War I said World War II, didn't I? It's World War I. He becomes the first person to exactly solve the Einstein equation. This man is in the trenches solving the Einstein equation. But yeah, so he wrote to Einstein with his findings in 1915, but unfortunately he died soon after, too soon to read what Einstein had written back. And by the way, what Einstein did say is that he was very impressed that Schwarzschild was able to solve it exactly, because he thought that you could only solve it approximately, but nope. So yeah, but anyways, back to the Schwarzschild solution. So if we look at this, so in the time-like component, we have -1 minus rs over r, where rs equals 2gm over c squared. And we're just going to be talking about these metrics in natural units, meaning that we're just going to pretend that c is equal to 1. So just pretend that rs equals 2gm. So we've got like -1 minus 2gm over r, et cetera, et cetera. So one thing that we can actually look at in the metric is the singularity of the black hole. So where in this metric is it going to be mathematically undefined? Well, when r equals 2gm, the r component becomes undefined. So like in the r component, if r equals 2gm, then we have 2gm over 2gm, so that's 1, and then we're 1 minus 1, so that's dividing by 0, so the r component becomes undefined. But however, this is not the actual singularity in the geometry of space-time. It's not this singularity, it's just a mathematical thing just because of how this coordinate system works. So yeah, but what this r equals 2gm does describe is the Schwarzschild radius, which is where the event horizon is at on your black hole. The real singularity is where r approaches 0. And when this happens, time blows up. So if we look at the time component, as r approaches 0, we're basically just going to be having a number over a very, very small number. So this is just going to totally blow up, going to approach infinity. And what does that mean physically? Who knows? Because it's a singularity. We don't know how to physically describe it. So yeah, that is an analysis of the Schwarzschild metric. But something that is kind of funny is that, remember what the Schwarzschild solution is: a description of a spherical object in a vacuum. It was meant to be an approximation of the space-time around spherical objects like stars. It wasn't derived by Schwarzschild for the purposes of describing a black hole. It was totally on accident that it describes a non-rotating uncharged black hole. In fact, at the time, no one, not even Einstein, realized that GR predicts black holes at all. It wasn't until the 1960s when people realized that GR predicts the existence of black holes, and the Schwarzschild solution is actually a description of non-rotating uncharged black holes. So that's kind of funny, but yeah. So that is the Schwarzschild solution. Moving on to the Reiner-Nordstrom solution. So the solution to Einstein's equations describing a spherically symmetric charged object was found in 1916 by Reiner and 1918 by Nordstrom. So this metric is actually going to be the exact same thing as the previous metric that we saw, except for in the time components and the radial components, we have this extra term, rq squared over r squared, where rq squared is just going to be basically the Q is the electric charge, and then this K, G over C to the fourth, all of that is just going to be a bunch of factors. So basically, we just have this term that is dependent on Q, the electric charge. So yeah. So again, Q is the electric charge and Q is the Coulomb constant. And same thing with this metric as it was with the Schwarzschild metric. Even though it wasn't the intention to describe a black hole, the Reiner-Nordstrom metric describes a non-rotating charged black hole. Moving on to the Kerr solution. This is the solution for a rotating uncharged black hole, and it was found by Kerr in 1963. So this looks like, it's a metric, all right. It looks like a bunch of garbage, but if you just look at what these variables, A, sigma, and delta represent, it's just, it becomes a little bit clearer. So whenever you see A, that is basically just in terms of the angular momentum and mass. Sigma is in terms of the radius and A, and then delta is in terms of the radius, the Schwarzschild radius, and the A. So I'm not even gonna analyze this because this is ugly. So moving on, the one thing that I am going to talk about with the Kerr metric is that we're used to seeing diagonal metrics where like the only values that are non-zero in the matrix are along the diagonal. But the Kerr metric has a cross term at G03, which is this element of the matrix right here. And this is because the black hole is rotating. Since these terms, these time-like terms, are time-like components, it's supposed to say time-like components, and these, wait, this is, I didn't even write the, wait. Oh, wait, no, sorry, yes, anyways. So, and G mu 3 are the space-like components down here. Crossing them indicates motion because it's kind of like, so you've got change in t with a change in position, kind of. I don't know if that makes sense, but having a cross term here between time and space indicates motion. And then if we look at this image of spherical coordinates, it makes sense why rotation is, for lack of a better term, a phi term, because phi is the angle by which it rotates around the axis. I hope that makes sense. So yeah, that is the Kerr solution describing a rotating non-charged black hole. And then the final solution is the Kerr-Newman solution. But before we look at it, we have to perform a coordinate transformation. So instead of using t, we're going to be using u. And so basically what we're going to be doing is u is equal to t minus this crap. I don't even know the explanation behind this. I just know it like basically just simplifies it. It makes it so that we can actually cleanly write the metric. But that is what we're going to do. We're going to do a coordinate transformation from t to u. So now we're working in the coordinates u, r, theta, and phi. So, oops. Okay, so this is the Kerr-Newman solution. This describes a rotating charged black hole, and it was found in 1965 by Newman. So this is it. Again, we're using the same terms, A, sigma, and delta, as we did with the Kerr solution. So again, a bunch of garbage, and again, some cross sections, because this time not only is it rotating, but it's also charged. And something that is cool is that if you set the charge equal to 0, so that it is rotating but is uncharged, you get the Kerr metric. And if you set the angular momentum equal to 0, you are going to get the Reisner-Nordstrom metric, because you're going to have a non-rotating charged black hole. And this is what you would expect, but it's just kind of cool to see that it still works mathematically. Okay, so a quick summary of this section that we just went through. So first of all, black holes are no hair, meaning that they can be described by just their mass, electric charge, and angular momentum. And then we saw these 4 metrics. The Schwarzschild metric, which describes a non-rotating uncharged black hole. The Reisner-Nordstrom metric, which describes a non-rotating charged black hole. The Kerr metric, which describes a rotating uncharged black hole, and the Kerr-Newman metric, which describes a rotating charged black hole. Okay, we only have 5 minutes left, and that was like half of the presentation. So hopefully we can go through this quickly, but we'll see. So now we're going into the different mass ranges of black holes and like the different types of black holes. So there are 4 types of black holes: stellar mass, intermediate mass, supermassive, and primordial. And these are all categorized by their mass ranges. So the stellar mass black holes have a range of 3 to 15 solar masses, or 3 to 15 times the mass of the sun. And these black holes form when a supermassive star or a neutron star collapses, becomes super dense. And then we have intermediate mass black holes, which have a mass of 100 to 1000 solar masses. And how these black holes form is unclear. So their masses have been found to be similar to that of globular clusters, which are just like clusters of stars, and small galaxies, which suggests that they might form there, but we don't really know. Another option is that they might form by merging stars, which collapse, or 2 merging stellar mass black holes. And then we have supermassive black holes, which are 10 to the 5 solar masses to 10 to the 9 solar masses. And these exist in the centers of most galaxies. So we have one in our galaxy. It's called Sagittarius A. And it is also unclear how these types of black holes form. Some possibilities is that they form when smaller galaxies merge, and their formation might be similar to that of intermediate mass black holes, but just like on a larger scale. And the famous black hole image is of a supermassive black hole in the galaxy Messier 87. So that's pretty cool. And then the final type of black holes are primordial black holes. And these have a mass of 10 to the negative 8 kilograms to 10 to the 5 solar masses. So that is a massive range. But yeah, so these black holes are ones that formed during the early universe. And these are only hypothetical because we haven't observed any yet, but if they exist, they might explain the origins of supermassive or intermediate mass black holes, because they might have just been kind of like the earlier versions of them. Now we're going to talk about what happens if you go inside a black hole? So I have this excerpt from a textbook that I was using as a reference for this presentation. I thought it just gave a nice, good explanation. So if you are watching from a distance, something go into a black hole. According to the distant observer, the radio photon will never reach the event horizon. Instead, according to gravitational time dilation, the photon's coordinate velocity will slow down until it finally stops at the event horizon in the infinite future. In fact, any object falling toward the event horizon will suffer the same fate. Seen from the outside, even the surface of the star that collapsed to form the event horizon would be frozen, and so a black hole is, in this sense, a frozen star. So basically, what it's saying is that when light passes the event horizon, it's not going to come out. So you're not going to see that image of something going into the event horizon. So from your perspective, the farthest that you can see is just right before it gets to the event horizon. So it's basically just going to, like it said, the photon's coordinate velocity will slow down until it finally stops at the event horizon in the infinite future. So it will never reach it from your point of view. So that is from the perspective of a distant observer. And then from the perspective of actually going in there, the gravity of the black hole will stretch you vertically and compress you horizontally as you are pulled in. And this is called spaghettification. And this might be intuitive from just looking at this image. You can see how like it would stretch you, you know? So yeah. And then we just have this little video, this artistic representation of what spaghettification looks like. Where's the video at? There it is. So you can see all of the star's mass that isn't getting sucked into the black hole is just getting flung off into space. So that is pretty cool. Okay, we only have a little bit left, but this is the last section. So I'm just gonna go over for a little bit. So the final section is on Hawking radiation. So Hawking radiation is the process by which black holes essentially evaporate over time. So from a classical standpoint, black holes would last forever because no information inside can escape. However, in 1974, Stephen Hawking theorized that there is a loophole to this using quantum physics. And so how this works is that in quantum physics, there is a process called pair production, where a particle and its corresponding antiparticle spontaneously appear due to, I'm being redundant, to fluctuations in energy in space-time. Ordinarily, these two particles almost instantaneously annihilate each other and disappear. But what if pair production occurs near a black hole's event horizon and only one of the particles falls in? The other particle goes off, just doing whatever, and it carries energy away from the black hole. Because this pair of particles was created from energy from the black hole's gravitational field, when the particle escapes, it takes some of the black hole's energy with it. And so over a very, very long time, this process reduces the black hole to a bunch of particles that are just going off, flying around in space. And this is just a little diagram of what's happening over here. So we have these pairs of virtual particles. And for this pair, this particle is getting sucked into the black hole and this other particle escapes. And this is the particle that is making up Hawking radiation. So the rate at which this energy is carried away is going to be equal to 1 over the mass of the black hole squared. Therefore, since the black hole is gradually losing its mass, the rate at which it evaporates increases over time. And so this final burst of evaporation is pretty explosive. It just kind of bursts. So yeah. So how long does this process take? So a black hole with the mass of our sun would take 10 to the 64 years. A black hole with a mass of 100 billion solar masses, which is like a supermassive black hole, would take 2 times 10 to the 100 years. So like 100 zeros. And then a black hole with a mass of 10 to the 11 kilograms, which is a primordial black hole, a really tiny one, would take only 2 times 6, 2.6 times 10 to the 9 years. And since primordial black holes can range from 10 to the negative 8 kilograms to 10 to the 5 solar masses, that's a pretty big range. Some observational astronomers are looking for signs of primordial black holes that are evaporating right now. So that is pretty cool. If they could find it, then that would be confirmation of these primordial black holes, and we would be witnessing Hawking radiation in process. So that is pretty cool. Okay, so everything that we covered today, or I guess we already went over the part about the 4 different solutions. So ever since then, what we have covered is there are 4 types of black holes. Stellar mass black holes, which form from collapsed stars, intermediate mass black holes, whose formation is unknown, possibly from the merging of small galaxies or globular clusters, supermassive black holes, which are the supermassive black holes in the center of most galaxies, and then finally primordial black holes, which are the smaller ones which formed during the very early universe. So, and then we had what happens if we go inside a black hole. Well, from a distant point of view, the object would never go past the event horizon. It would just very, very slowly approach it, but never reach it. It would only reach it after an infinite amount of time. And then from an insider point of view, you would get spaghettified and die pretty quickly, even before a long time before you reach the event horizon. And then finally, we had Hawking radiation, which is the process by which black holes evaporate. And this happens via pair production, where one particle falls inside the black hole and one escapes, carrying the black hole's energy away with it. So that is it for black holes. Yeah, I'm going to stop the recording now. Where is it?